Is reality about to change? This revelation will shock you. What if everything you believe about reality is only a fraction of the truth? What if the solid ground beneath your feet, the sky above your head, even time itself are not as fixed and reliable as they seem? For centuries, humanity has tried to understand the nature of reality. We built philosophies, religions, and scientific frameworks to explain the world around us. We believed reality was solid, measurable, predictable. But the deeper we look, the stranger it becomes. Modern physics tells us that matter, the very substance of everything, is mostly empty space. The atoms that form your body, the chair you sit on, the planet you stand upon, are vast fields of energy with tiny vibrating particles. Solidness is an illusion created by forces interacting at microscopic levels. Quantum mechanics goes even further. It suggests that particles can exist in multiple states at once. That observation itself can influence outcomes. That reality, at its most fundamental level, behaves not like a machine, but like a probability. Think about that. If observation affects reality, then consciousness may not just be a passive witness, it may be a participant. For decades, this idea sounded like science fiction. Today, it is serious scientific discussion. Researchers are exploring whether space-time itself emerges from deeper informational structures. Some propose that reality may be more like a simulation, a dynamic system of encoded information rather than a fixed physical stage. And then there is the cosmos. We now know the universe is expanding, not slowly, but accelerating, driven by something we call dark energy. Yet we do not know what dark energy truly is. In fact, everything we can see, stars, galaxies, planets, makes up less than 5% of the universe. The rest is dark matter and dark energy, invisible and mysterious. We are living inside a reality that is mostly unknown. So ask yourself, if 95% of the universe is invisible to us, how complete is our understanding of reality? But here is where it becomes truly astonishing. New discoveries in quantum gravity, consciousness research, and cosmology are converging toward a radical possibility. Reality may not be fundamental. It may emerge from something deeper, information, frequency, geometry, or even awareness itself. If this is true, then reality is not a rigid structure. It is dynamic, responsive, evolving, and that changes everything. It changes how we see life. It changes how we see death. It changes how we see ourselves. If reality is participatory, then our thoughts, our intentions, our perception may play a more significant role than we ever imagined. If space and time are not fixed, then the boundaries we assume may not be ultimate. This is not mysticism replacing science. This is science pushing so far into the unknown that it begins to challenge our most basic assumptions. Throughout history, every major revelation has reshaped humanity's worldview. The Earth was not the center of the universe. Time was not absolute. Space could bend. Now we stand on the edge of another shift, a shift where reality itself may not be what we thought it was. The question is not whether reality is changing. The question is whether our understanding of it is finally catching up. And if this revelation proves true, if reality is deeper, stranger, and more interconnected than we ever believed, then we are not just observers in a cold, mechanical universe. We are participants in a living, unfolding mystery. And that realization may shock the world. Reality, as we experience it through our senses, appears solid, stable, and unquestionably physical. We touch objects and feel resistance. We walk on the ground and trust it will support us. We see buildings, mountains, oceans, and stars, and we assume they are fundamentally made of solid substance. For most of human history, this assumption seemed obvious and unquestionable. Matter was thought to be composed of tiny, indivisible particles, hard, solid building blocks forming everything in existence. But as science advanced and we began to look deeper into the structure of matter, this certainty started to dissolve. When physicists first explored the atom, they expected to find compact, solid units. Instead, they discovered something astonishing. Atoms are not solid spheres. They are mostly empty space. At the center lies a nucleus, incredibly small compared to the total size of the atom, surrounded by electrons that do not orbit like miniature planets, but exist in probability clouds, regions where they are likely to be found. If the nucleus were the size of a marble placed at the center of a stadium, the electrons would be tiny specks moving around the outer edges, leaving vast emptiness in between. This means that everything we perceive as solid, the walls, the ground, our own bodies, is composed primarily of empty space. The sense of solidity arises not because matter is densely packed, but because of electromagnetic forces. When you press your hand against a table, the electrons in your hand repel the electrons in the table. You are not truly touching the table in a classical sense. You are experiencing force interactions between energy fields. At an even deeper level, the particles within atoms, protons, neutrons, and electrons are not solid objects either. They behave both as particles and as waves. This wave-particle duality suggests that what we call matter is not strictly material in the traditional sense. It has properties of vibration, frequency, and probability. Electrons can behave like ripples of energy rather than tiny balls of substance. The foundations of physical reality begin to look less like solid bricks and more like dynamic patterns. Quantum field theory goes further. According to this framework, the universe is not made of particles at its most fundamental level. Instead, it is made of fields, continuous entities that exist everywhere in space. What we call a particle is actually a localized excitation of a field, similar to a wave forming on the surface of water. An electron is not a tiny object traveling through space. It is a vibration in the electron field. A photon is a vibration in the electromagnetic field. Matter itself emerges from these underlying fields of energy. This radically shifts our understanding. If particles are merely excitations of fields, then matter is not fundamental. Energy fields are. The solid world around us becomes a complex interaction of vibrating fields, constantly fluctuating and exchanging energy. Even in what we consider a vacuum, empty space, quantum fluctuations occur. Virtual particles appear and disappear in fleeting moments. Space itself is alive with activity at microscopic scales. Einstein's famous equation E=mc2 revealed that mass and energy are interchangeable. Matter can be converted into energy, and energy can manifest as matter. This equation is not abstract theory. It is demonstrated in nuclear reactions and particle accelerators. The implication is profound. Matter is a condensed form of energy. The distinction between solid substance and dynamic energy begins to blur. As research advances, some physicists suggest that information may be even more fundamental than energy. The behavior of quantum systems is described by mathematical wave functions representing probabilities and informational states. In certain interpretations, reality is structured like a vast informational network. Space, time, and matter may emerge from deeper layers of encoded relationships. Black hole physics has strengthened this idea. The holographic principle proposes that the information describing a volume of space may be encoded on its boundary, much like a hologram. If correct, the three-dimensional world we experience could arise from two-dimensional informational structures. When we combine these discoveries, the traditional picture of a solid mechanical universe collapses. Instead of a static world made of rigid objects, we find a dynamic system of energy fields and informational patterns. Stability arises from continuous motion and interaction. What appears fixed is actually in constant flux. At the atomic level, particles flicker, vibrate, and exchange forces at unimaginable speeds. Even time and space may not be fundamental. Some theories of quantum gravity suggest that space-time itself emerges from more basic quantum relationships. If space and time are emergent, then the stage on which reality unfolds is not absolute. It is a constructed framework arising from deeper processes. This perspective challenges our intuition because our senses evolved to perceive stability. The brain interprets electromagnetic signals as solid color and texture. It filters complexity into coherent objects. But beneath that simplified perception lies an ocean of energy interactions. The chair you sit on is not a static object. It is a temporary arrangement of vibrating fields maintaining a stable pattern. In this view, reality resembles music more than machinery. It is a symphony of frequencies interacting in harmony and tension. Atoms bond because of electromagnetic resonances. Chemical reactions occur through energy exchanges. Light itself is oscillating electromagnetic waves traveling through space. Everything is vibration at different scales and intensities. The implications extend beyond physics. If reality at its core is energy and information, then our understanding of existence must expand. The separation between objects becomes less absolute. All matter arises from the same underlying fields. The diversity we see, stones, trees, animals, stars, emerges from variations in frequency and arrangement. Unity underlies apparent difference. Scientific instruments continue to probe deeper into subatomic structure, revealing layers of complexity. Particle accelerators smash particles together, converting matter into bursts of energy and discovering new excitations of quantum fields. Observatories detect gravitational waves, ripples in space-time caused by massive cosmic events. Each discovery reinforces the idea that reality is not built from solid blocks, but from dynamic processes. The world we perceive is stable only because these processes maintain equilibrium at macroscopic scales. At microscopic levels, constant motion and transformation occur. Stability is an emergent phenomenon arising from countless interactions balancing one another. Solidity is not a fundamental property. It is a collective effect of energy fields interacting according to physical laws. As our models improve, the language of physics increasingly centers on vibration, frequency, and encoded relationships. The notion of solid matter fades into abstraction. What we once called substance is now understood as structured energy. The universe becomes a vast, interconnected system of fields, oscillations, and informational exchanges operating across scales from the subatomic to the cosmic. For centuries, consciousness was treated as a passive phenomenon, a byproduct of brain activity, a silent observer watching the physical universe unfold. The dominant scientific model described reality as a machine operating independently of awareness. Stars burned, planets moved, atoms collided, and life evolved according to fixed laws. Human consciousness simply emerged within this system, like steam rising from a boiling pot. It observed but did not influence the deeper structure of reality. Yet as physics ventured into the quantum realm, this assumption began to crack. In quantum mechanics, the act of measurement plays a strange and central role. Experiments such as the double-slit experiment reveal that particles like electrons behave differently when observed. When unmeasured, they act like waves spreading out in patterns of probability. When measured, they behave like localized particles. The mere act of observing seems to affect the outcome. This phenomenon has been repeated countless times under rigorous laboratory conditions. The mathematics predicts it and experiments confirm it. At the quantum level, observation is not neutral. This does not necessarily mean that human thought magically reshapes the universe at will. However, it does suggest that interaction with a measuring system collapses a range of possibilities into a single outcome. Before measurement, a particle exists in a superposition of states, multiple potential realities coexisting mathematically. Upon observation, that superposition resolves into a specific result. The question that continues to provoke debate is what exactly constitutes an observation? Is it any physical interaction? Is it information exchange? Or does consciousness itself play a role in finalizing outcomes? Some interpretations of quantum mechanics argue that consciousness is fundamental to the collapse of the wave function. According to this perspective, Reality does not solidify into definite form until it is observed by a conscious entity. Other interpretations avoid invoking consciousness directly, suggesting instead that environmental interactions cause decoherence. Yet even decoherence theory does not eliminate the mystery entirely. It explains how quantum systems appear classical, but it does not fully explain why a specific outcome emerges from probabilities. The philosophical implications are profound. If observation is essential in shaping measurable reality, then consciousness may not be an accidental byproduct of matter. It may be woven into the fabric of how the universe manifests. The traditional view places consciousness inside the universe. A growing number of thinkers explore whether the universe may, in some sense, exist within consciousness, or at least be inseparable from it. Neuroscience adds another layer to this discussion. The brain does not passively record reality like a camera. It actively constructs experience. Sensory data enters as electrical signals, and the brain interprets these signals into images, sounds, textures, and meaning. What we perceive is not raw reality, but a model generated internally. Color does not exist outside as we see it. It is the brain's interpretation of electromagnetic wavelengths. Sound is the brain's rendering of air vibrations. Even the sense of time passing is a neurological construction. If perception is an internal construction, then our experience of reality is already shaped by consciousness at a fundamental level. We do not experience the world directly, we experience our interpretation of it. This realization blurs the boundary between external reality and internal awareness. The world we navigate daily is inseparable from the way our minds organize and process information. In physics, the role of the observer challenges the idea of a completely objective universe. In psychology and neuroscience, perception demonstrates that subjectivity is unavoidable. Some researchers explore whether consciousness could be more than neural computation. Theories such as integrated information theory propose that consciousness arises from systems capable of integrating information at high levels of complexity. Other approaches like panpsychism suggest that consciousness may be a fundamental feature of reality, present in rudimentary form even at basic physical levels. Cosmology also enters this conversation. The universe appears finely tuned for the emergence of life and observers. Physical constants lie within narrow ranges that allow complex structures to form. The anthropic principle suggests that we observe these conditions because only such a universe permits observers. Yet some thinkers speculate whether observation itself plays a role in selecting among possible universes. In certain interpretations of quantum cosmology, the presence of observers influences which histories become actualized. Beyond theoretical physics, experiments in quantum entanglement demonstrate that particles can remain correlated across vast distances. Measuring one particle instantaneously influences the state of another, regardless of separation. While this does not allow faster-than-light communication, it reveals deep, non-local connections within reality. The universe at its most fundamental level appears interconnected in ways that defy classical intuition. Conscious observers are part of this interconnected web. Meditative traditions and contemplative practices have long claimed that consciousness shapes experience more deeply than we realize. While science approaches the subject cautiously, research into neuroplasticity shows that thoughts and focused attention can physically rewire the brain. Intentional mental training alters neural pathways, emotional responses, and perception patterns. The boundary between mind and matter is not rigid. Mental states produce measurable physical changes in brain structure. The placebo effect further illustrates the influence of belief and expectation on physical outcomes. Patients receiving inert treatments sometimes experience genuine physiological improvements simply because they believe they are being treated. Brain imaging shows real biochemical changes accompanying these effects. Expectation, a product of consciousness, influences bodily processes in tangible ways. None of this implies that consciousness can arbitrarily override physical laws. The universe operates according to consistent principles. However, these discoveries collectively suggest that consciousness is not merely a detached spectator. It interacts, interprets, and possibly participates in shaping the unfolding of events at certain scales. As research progresses, interdisciplinary studies attempt to bridge physics, neuroscience, information theory, and philosophy. Some models describe reality as fundamentally informational, with consciousness representing a specific form of information processing within that system. Others propose that awareness is a basic ingredient of existence alongside space, time, and energy. The emerging picture is complex and incomplete, yet it consistently challenges the simplistic notion of a purely mechanical universe observed by passive minds. Instead, reality appears relational. Observation, measurement, and awareness are embedded within the structure of physical processes. The line separating observer and observed becomes less distinct. Consciousness participates in defining experience, shaping perception, and possibly influencing how potential states resolve into experienced events within the unfolding fabric of existence. For most of human history, the night sky appeared complete. The stars, the moon, the wandering planets, and the glowing band of the Milky Way seem to represent the entirety of existence. With the invention of telescopes, we realized our galaxy was only one among billions. With modern observatories and satellites, we mapped clusters of galaxies stretching across unimaginable distances. Yet as our instruments became more powerful, a humbling realization emerged. Everything we can see, every star, planet, nebula, and galaxy accounts for only a small fraction of the universe. Precise measurements of cosmic motion revealed something astonishing. Galaxies rotate at speeds that cannot be explained by the visible matter they contain. According to Newtonian physics and Einstein's general relativity, the outer edges of galaxies should spin more slowly than the inner regions, much like planets in a solar system. Instead, they rotate almost uniformly. The gravitational pull required to hold these galaxies together must be far stronger than what visible matter can provide. This missing mass was given a name: dark matter. Dark matter does not emit, absorb, or reflect light. It cannot be seen directly. Its presence is inferred from gravitational effects. It shapes the motion of galaxies, bends light through gravitational lensing, and influences the large-scale structure of the cosmos. Without dark matter, galaxies would not have formed the way they did. Vast cosmic webs, filaments of matter stretching across space, owe their structure to this invisible component. Current estimates suggest that dark matter makes up about 27% of the universe. Even more mysterious is dark energy. In the late 1990s, astronomers studying distant supernovae discovered that the expansion of the universe is accelerating. For decades, scientists assumed that gravity would gradually slow cosmic expansion. Instead, galaxies are moving away from each other at increasing speeds. Something is pushing space itself to expand faster over time. This unknown force was labeled dark energy, and it appears to constitute roughly 68% of the universe. When we combine these figures, the implication is staggering. Ordinary matter, the atoms that form stars, planets, oceans, and human beings, makes up less than 5% of the total cosmic content. The vast majority is invisible and poorly understood. The universe we observe directly is a thin surface layer covering a much deeper reality. Dark matter remains elusive despite decades of research. Scientists have built underground detectors shielded from cosmic radiation, hoping to capture rare interactions between dark matter particles and normal matter. Particle accelerators attempt to create candidate particles under extreme conditions. So far, direct detection has not been confirmed. The leading hypotheses suggest dark matter may consist of weakly interacting massive particles, axions, or other exotic entities predicted by extensions of the standard model of particle physics. dark energy presents an even greater challenge. Some theories associate it with the cosmological constant, a property of space itself. In this view, empty space is not truly empty, but possesses intrinsic energy that drives expansion. Other models propose dynamic fields that change over time. Theoretical calculations of vacuum energy, however, produce values vastly larger than what is observed, creating one of the greatest discrepancies in physics. The cosmic microwave background radiation, the faint afterglow of the Big Bang, provides additional clues. Detailed measurements of its temperature fluctuations reveal patterns that align with a universe dominated by dark matter and dark energy. These observations allow scientists to estimate the universe's age, composition, and geometry with remarkable precision. Yet precision does not equal understanding. We can measure effects without fully comprehending causes. The existence of such a large, unseen component forces us to reconsider our place in the cosmos. The visible universe, the one accessible to telescopes and human senses, is not the whole story. It is a minority component within a much larger framework. The structures we observe are shaped by forces we cannot directly perceive. Gravitational lensing offers dramatic evidence of this hidden reality. Massive clusters of galaxies bend light from objects behind them, acting like cosmic magnifying glasses. By analyzing how light curves around these clusters, scientists map the distribution of dark matter. These maps reveal massive halos extending far beyond visible galaxies, confirming that what we see is embedded within vast, invisible structures. Simulations of cosmic evolution further emphasize the role of dark matter. When researchers model the universe using only ordinary matter, galaxies fail to form correctly. When dark matter is included, large-scale structures emerge that closely resemble observed distributions. Dark matter acts as scaffolding, providing gravitational wells into which ordinary matter falls, eventually igniting stars and forming galaxies. Despite these advances, fundamental questions remain unanswered. What is dark matter made of? Why does dark energy have the specific strength it does? Are these phenomena related or entirely separate? Some theories propose modifications to gravity itself rather than new forms of matter. Others explore higher dimensional models in which our universe is part of a larger multiverse structure. The realization that 95% of the universe is invisible reshapes scientific humility. It reminds us that current knowledge, though impressive, is incomplete. Every technological leap, from radio telescopes to space-based observatories, has revealed layers of reality previously hidden. Future instruments may uncover properties of dark matter or detect subtle variations in dark energy. This hidden majority also influences cosmic destiny. If dark energy continues accelerating expansion indefinitely, galaxies will drift beyond each other's observable horizons. The night sky, billions of years from now, could appear empty to distant observers. Alternatively, if dark energy changes over time, the universe's fate could differ dramatically. The ultimate trajectory depends on forces we are only beginning to investigate. The recognition that most of existence is unseen transforms our understanding of reality. It expands the scope of inquiry and challenges assumptions about completeness. What appears stable and luminous is supported and influenced by vast, silent components operating beyond direct detection. The visible cosmos floats within an ocean of mystery, structured by gravitational forces and expansive energies that remain largely undefined within the current framework of physics.